Semantic analysis means figuring out what a program means. For example, the semantic analysis phase of compilation recognizes when multiple occurrences of the same identifier are meant to refer to the same program entity, and ensures that the uses are consistent. In most languages, the semantic analyzer tracks the types of both identifiers and expressions, both to verify consistent usage and to guide the generation of code in later phases. The semantic analyzer typically transforms the parse tree into an abstract syntax tree by removing most of the artificial nodes in the tree's interior. The semantic analyzer also annotates the remaining nodes with useful information, such as pointers from identifiers to their symbol table entries. In many compilers, the annotated syntax tree constitutes the intermediate form that is passed from the front end to the back end. To assist in its work, the semantic analyzer typically builds and maintains a symbol table data structure that maps each identifier to the information known about it. Among other things, this information includes the identifier's type, internal structure, if any, and scope, the portion of the program in which it is valid. Using the symbol table, the semantic analyzer enforces a large variety of rules that are not captured by the hierarchical structure of the context-free grammar in the parse tree. In C, for example, it checks to make sure that every identifier is declared before it is used, no identifier is used in an inappropriate context, such as calling an integer as a subroutine, that subroutine calls provide the correct number and types of arguments, and any function with a non-void return type returns a value explicitly. You should note that not all semantic rules can be checked at compile time. Semantic rules that can be checked at compile time are referred to as the static semantics of the language. Semantic rules that must be checked at runtime are referred to as the dynamic semantics of the language. C has very little in the way of dynamic checks because its designers opted for performance over safety. Examples of rules that other languages enforce at runtime include variables are never used in an expression unless they have been given a value, and an array subscript expression lies within the bounds of the array. When it cannot enforce rules statically, a compiler will often produce code to perform appropriate checks at runtime, either aborting the program or generating an exception if one of the checks fails. In the extreme case, some rules can be either too expensive or completely impossible to enforce, and the language implementation may simply fail to check them. In C, a program that breaks such a rule is said to be undefined.